Now next we move on to the measures of relative dispersion or spread. And the first one is the range. Then we'll look at the interquartile range, and then we'll look at z-scores. Now the range we haven't counted before. It's simply the maximum value in the dataset minus the minimum value. And that's it. We saw this with the construction of the histograms. Secondly, it uses only two values in the dataset. And the disadvantage is that it uses the two most extreme values in the dataset. It uses the maximum and the minimum. So if we have a dataset where almost all the values are very close together, but we have a really small value and a really large value, and we calculate the range, it's going to appear as if the data is spread over a very big area. But it's just the two extreme values that's creating this impression. Most of the values is actually very close together. So that's why the range is severely affected by extreme values. So we can say that the range is not robust. Okay, it is not robust. It is easily affected by extreme values. The interquartile range, that's a new one, but think of range as taking a large value and subtracting a small one. Interquartile, which means we're working with quartiles, so we'll take the largest quarter, or largest quartile rather, and we'll subtract the smallest quartile, which is what we do for a range, maximum minus minimum. So quartile range, we'll take the maximum quartile minus the minimum quartile. The advantage of this, it is more resistant to outliers. So in other words, where this one is not robust, the interquartile range is robust. Because remember, extreme values or outliers are at the ends of a data set. The third quartile and the first quartile, they are not at the ends. Right, and we also use this in box plots to detect outliers. Right, now finally, z-scores is calculated by taking each observation, whether it's a sample or whether it's a population, it doesn't matter. You take each observation, you subtract the mean from it, and then you take that result and you divide by the standard deviation. So if it's for a sample, you'll subtract x bar, divide by s. If it's for a population, you'll subtract mu and you'll divide by sigma. Remember, population parameters are Greek letters, whereas sample statistics are not. Now, the nice thing about a z-score, it is a unit-free measure of distance. Okay, unit-free. In other words, it's not affected by whatever units you are using in your dataset, whether it's kilometers or meters or whatever the case is. It's not affected by it. Now, what it actually does, if we look at the calculation itself, we're taking the distance between a value and the mean of the dataset, and we're dividing it by the standard deviation. Okay, whether it's sample or population, we're dividing that distance by standard deviation. So that means what we're actually calculating is we are actually calculating how many standard deviations lie between the x value that we are using and the mean. So in other words, how many standard deviations away is the value x from the mean of the population or the sample. Right, and then this actually not only measures that distance, but we can use it in our empirical rule, which we'll look at just now. We can use it in our empirical rule to detect outliers. Because outliers are extreme values, whether it's very small or very big, they don't conform to the rest of the values, and using this method we can actually identify them. Right, now next we have our box plot, which is also called the box and whisker plot. Now the box plot is a graphical summary, and it is one of the very first graphical summaries that one would use when you analyze data, because it is a very nice graphical summary that immediately identifies any extreme values, in other words any outliers, because outliers can have a severe effect on the analyses of the data. It can make the analysis unreliable. So we would like to identify outliers first and address the outliers. It could be that the outliers are actually true values, that's supposed to be there, but it could be that the outliers might be a mistake when the data was captured. For example, if you miss a decimal point in a data set, then you will immediately have an outlier where most of the values might be around, let's say 2.5, 2.6. If you miss a decimal, then suddenly you have a 25 or a 26. So the box plot helps us to identify situations like that. It uses basically 5 numbers: the minimum, the 3 quartiles, and then the maximum. But there are other values that we need to calculate as well for the box plot, and those are 4 other values, which are boundary values. But we'll have a look at them just now. Right, and then lastly over here, the box plot is also very useful for comparing distributions, and we'll look at an example of that as well. Right, now in order to construct the box plot, as you saw here, we need the 3 quartiles. Now this is the dot plot that I had earlier on, and I had indicated the quartiles on there. So all that I need to do now is to actually literally draw a box using those quartiles. So in the first quartile, I'll have a vertical line, the second quartile and the third quartile, and then I'll create a box from those 3 lines. And then I will have the whisker part. That's where the second part of the name comes from, box and whisker. And I'll have a whisker going from Q3 up to the maximum, and a whisker going from Q1 all the way down to the minimum. If I take away all the other things, and only the box plot remains, then this is what I have. And I don't write the percentages there. We should know that this is exactly what it means. So when you see a box plot like this, you should know that this is the first quarter, well, first quartile, second quartile, third quartile, and that this whisker here represents 25%. This left side of the box, 25%, 25% for the right side of the box, and 25% for the right whisker. Now, as we saw previously, remember I've been working with this data set now for a few examples. If I just resize this so we can see, then this was the histogram that I constructed for this data. And we identified this histogram as being negatively skewed, in other words, skewed to the left. So if we look at the box plot, then we see that this long whisker on the left actually means negatively skewed, along with this large left-hand box. The right side box is also 25%, but it's very compressed, and this whisker is also very short. So 50% of the data on the right covers a very small area, whereas 50% of the data on the left covers a huge area compared to the others. So that's why we can say that it's negatively skewed. So if we look at these are 4 box plots for 4 different data sets illustrated on the same axes. But we can actually comment now on the shape of the distribution by looking at the box plots. Obviously this one will be positively skewed because we have a very long spread out 50% on the right, and we have a very short 50% on the left. The same for the second one. This 50%, the first 50% of the data, covers a smaller area than the right 50%. So we can think of this one as also being slightly positively skewed. And the same with the third one over here. This 50%, smaller distance than this 50%. So it's slightly positively skewed. This one over here, the 50% on the left is almost the same as the 50% on the right. So this, and the boxes as well, is almost split exactly in half. So this seems to be symmetrical. Right, so from the box plot, we should be able now to make comments like this regarding the data set. Right, now next, I said that we need to extend this 5-number summary because it isn't really sufficient for detecting outliers. Remember, an outlier is an extreme value. It's either the smallest or the largest values in the data set. If we have a whisker going right down to the smallest, and we have a whisker going right up to the largest, we don't know whether those are outliers. We need some criteria in order to determine whether they are extreme or not extreme. So what we do is we construct boundaries or fences. We have fences that we'll construct on the left, and we'll have fences that we construct on the right. Now these fences or boundaries are cutoff points that give us an indication of whether a value is extreme or whether it is not extreme. So on the left side, we will have a lower outer fence and a lower inner fence. On the right, we'll have the same. We'll have an upper outer fence and an upper inner fence. If a value is greater than the outer fence, then it's definitely an outlier. If it lies between these two fences, we call it a suspected outlier. And the same over here. If it's below the lower inner fence, but still not below the lower outer fence, it'll be a suspected outlier. If it's right down here below the outer fence, then it's definitely an outlier. And everything in between here will be everything in between there. So that's the bulk of the data. Right, now the lower outer fence is calculated by taking the first quartile and subtracting 3 times the interquartile range. The lower inner fence, the position will be the first quartile again, and I'm subtracting 1.5 times the interquartile range. So obviously for the upper inner fence, I will take Q3 now, and I will add 1.5 times the interquartile range. Here I took Q1 and I subtracted 1.5 times the interquartile range. In other words, from there, I went down to find the lower inner fence, and then I went down even further to find the lower outer fence. On this side, from there, Q3, I'm going up to find the upper inner fence, and then up again to find the upper outer fence, which will be Q3 plus 3 times the interquartile range. So when I do this calculation for each one, we'll see that the lower quartile, Q1, 142.5, the interquartile range is 85. 3 times that, subtract, I get minus 112.5. So the lower outer fence is at minus 112.5, but my smallest value on my data set is only 0. So the lower fence is sitting right down here somewhere. So it's irrelevant. I can really just ignore it. The lower inner fence is sitting at 15. It's Q1, which is 142.5, minus 1.5 times the interquartile range. Now 15, if that's 70, then about 35 will be over there. So that means 17.5, and let's say 15 will be over there. 0 is the smallest value in my data set. 0 is actually between these two values. So 0 is sitting over there. So that means that 0 is a suspected outlier. In other words, it doesn't really conform to the rest of the data. On the right hand side, I have the upper inner fence, which is Q3, plus 1.5 the interquartile range. That gives me 355. Now 355 is much bigger than the largest value in the data set, which is 290. 355 is going to be off my screen here actually. So that means the upper outer fence is even bigger than that, because here I add 3 times the interquartile range, and it's at 482.5, so it's going to be even further away. So I can actually just ignore these two for this example, because the largest value in my data set, 290, is well below the upper inner fence. So there's no suspected or outliers on the right hand side, right? So no really large values in the data set. Right, so if I indicate the lower inner fence or the lower inner boundary, then outliers will lie between, or outliers on the left will be less than minus 112.5. Suspected outliers will be less than 15, and we saw that this is in fact 0. And suspected outliers on the right will be greater than 355, but definite outliers will be greater than 482.5. And so for my example, I only have 0, which is a suspected outlier, since it lies between these two fences over here. Right, lastly, we have our z-scores. Now this is a really simple calculation, very straightforward, very easy to understand. If we look at the data set that I've been working with the whole time, x1 to x20, no specific order, then I need two sample statistics, which is x bar and s, in order to calculate the z-score for my sample. If I take x10, for example, okay, x10 is 290, and that means I'll take 290, I'll subtract 186 from it, and I'll divide that answer by 71.46. So this is 1.46 s. Okay, this is an s. And we'll say that it's x10 is 1.46 standard deviations from the sample mean. The fact that 146 is positive means that x10 is 1.664 or 1.46 rather standard deviations above the sample mean. If this was negative 1.46, then it would mean that x10 is 1.46 standard deviations below the sample mean. Okay, so this is telling me the distance that x is from the mean, but not just any distance, it is actually measuring that distance in terms of standard deviations. For a population, remember just these values change from statistics to parameters. Mu is the population mean. The calculation we saw earlier on is exactly the same as for the sample mean, so that's why we get 186 and 186, because for the sake of the example, I'm treating this now, my data set, as a population. The only thing that will be different is the standard deviation, because remember in this calculation for the sample standard deviation, I divide by n minus 1, whereas here I divide by n. So that means my answer here will be smaller because I'm dividing by a bigger value. So if I'm looking at calculating the z-score for x10 in this case again, now it's going to be 1.49 sigmas. In other words, if this was a population, then x10 would be 1.49 standard deviations above the mean. I'm saying above because this is positive. Right, so z-scores just measures the distance of a value from the population or the sample mean, and that is why with my example that I started off with, if you have 64 compared to a population average of 50, then it's good, but if you have it compared to a population average of 82, then it's bad because you're lying below the average. Right, now lastly, I want to look at the empirical rule. And the empirical rule is really important, and it's very easy as well. But we do need to recall some things that we discussed in previous sections. Now what it says is that for nicely shaped distributions, what do we mean by nicely shaped? Well, first of all, the data must be unimodal. Okay, so we have unimodal data. It mustn't be too skewed, and it mustn't have too long or too short tails. Now, the nicely shaped distributions that we usually refer to are ones that are bell-shaped. If you can't remember the bell-shaped, then go back to the measures on location and dispersion to see the different distributions over there. Right, so if we have a nicely shaped distribution that has these three properties, then what we'll find is that 68% of the data lie within one standard deviation of the mean. So the mean will be the middle point, whether it's a sample or whether it's a population, it doesn't matter. If the distribution is symmetrical, then the mean will always be in the middle. Okay, listen carefully. If the distribution is symmetrical, so if we fold it in half, then the two halves fit on top of each other perfectly. If the distribution is symmetrical, the mean, median, and the mode will always be in the middle, okay, if it's unimodal as well. If we add one standard deviation, and if we subtract one standard deviation, then this interval that we create on the x-axis will contain 68% of the data. Now please remember, this 68% that's colored over here, it's not the data. The data does not float around in here. The data are the values that is indicated on the x-axis. So 68% of the data will be indicated there. This 68% just tells me how much. In other words, the height of the bars. If you go back to graphical summaries of data, specifically the histogram and the frequency polygon, then you'll recall that I mentioned there, percentage is really important. We should be thinking of the area under the curves or under the bars of the histogram as a percentage. So this just means that if I were to have a histogram here and I were to add the percentages for all the different bars in the shaded area, then these percentages will add up to 68% of the data. And obviously because this is symmetrical, this is going to be 16% and this is going to be 16%, so that when we add everything up, we get 100%. Okay, because all the observations will be on this axis over here, and the height of the bars for the histogram tells me how many observations I have. But I can't have any observations anywhere else on the number line, because the histogram and the polygon is only constructed for the interval where I actually have the data. Right, so this is the one standard deviation rule. Okay, for the empirical rule, adding and subtracting one standard deviation to and from the mean, I have an interval for 68% of the data. If I add and subtract two standard deviations now, whether it's the mean for the sample or population, it doesn't matter. Adding and subtracting two standard deviations gives me an interval, and that interval now contains 95% of the data, but only if the polygon or histogram has those three properties. And if I extend it to three standard deviations, then I'll have 99.7% of the data. So that means almost 100% of the data will lie within three standard deviations of the mean. Right, please note this empirical rule is really important, and it will be coming up again in the later section when we discuss the normal distribution.